Hey, Al, can you hear me? Awesome. If you could just go ahead and get your PSU IDs in the chat box, that would be really helpful for me. Just so that I can tell my bosses that people do show up to these sessions. And then we can go ahead and get started. Thank you. Book, and I can't find it, so it goes. I'll actually just kind of like open the floor up to you all right now, if that's okay. Usually when I do midterm reviews, I just kind of make sure that everybody's on the right page. Let's do what people need to do. Do you guys have any questions? Kind of hard to prepare for this just because everyone stumbles on different things in studying these midterm exams. So I just want to make sure you guys. For me, what worked best was to just do about 1 million practice problems, which is super, super time consuming, but when I was taking the class the first time, and what I've recommended to students in the past is to just practice, practice, practice until you like look at a problem and you feel confident in approaching it. Inflection points, let's totally do that. Let's do one of those problems where, if it's okay with you, I know that professors really like these, where they give you like an equation and then they ask you like critical points, inflection points, and min-maxes, and then they ask you to draw the function. And I'm going to do that as soon as I find my book, which I apparently can't find. Give me just a few seconds to track it down. Here we go. Let's do some inflection points. Oh, gotcha. Yeah. Do you struggle with that when they're asking, like, can you find an inflection point, like, et cetera, or like when you're trying to, like, what type of problems are you thinking of when you say knowing the difference between the first and second derivatives, or when to use them? Checking concavity. Gotcha. Problems. Chapter. Thank you. Yes. Okay. Well, the general rule that I'm going to tell you to follow there is that if you're checking for concavity, you're going to be checking the second derivative. If you're checking for increasing and decreasing, you're going to be checking the first derivative. And that is essentially, and that would be the sign of the first derivative and the sign of the second derivative. Where is section 3? Sorry. Okay. Section I wanted to go to. Okay. And then, yes, so general rule, if you're asked to find the absolute min and max, you're going to plug in x is equal to the critical point, and x is equal to endpoints into f of x. If you need to know the like x location of local mins and maxes, that is going to be x is equal to the critical point. If you need to know increasing and decreasing, going to be looking at sine of our first derivative, f prime of x. And if you're looking at concavity, you're going to be looking at the sine of the second derivative. So you're going to need to find the critical points in order to get this absolute min and max. But you are going to be plugging all of that information into the original function. And again, you're going to need to use the first derivative to find the critical points. Okay. Why don't we start off with something like 35 in section 3.3. Squish the book a little bit. And 3.3 right now. We're going to get the function f of x is equal to 1/2 x to the 4th minus 4x squared plus 3. Okay, so for this problem, they're going to have us find the intervals of increasing and decreasing. They're going to have us find all local maxes and mins, the intervals of concavity, and then they're going to ask us to sketch. So, step 1, what do we want to do? What is the first thing that you all would do to solve this problem? Take the derivative. How are we going to take the derivative? It's just going to be the power rule. Yep. So this is going to be 2x cubed minus 8x plus 0. So here's my derivative. What's next? Yep. Feel free to just, yes, okay. So to find a critical point, we're going to set f prime of x equal to 0, which is equal to 2x times x squared minus 4. And if 2x times x squared minus 4 is equal to 0, that means that 2x must be equal to 0. Or x squared minus 4 must be equal to 0. So if 2x equals 0, then x equals 0. And if x squared minus 4 equals 0, then x squared is equal to 4. And x is equal to plus or minus 2. So we have our critical points here. Put right here. So make this big. I can zoom. So our critical points are going to be x is equal to minus 2, x is equal to 0, x is equal to 2. Does everybody understand how we found those? Everybody cool? Awesome. Okay. So, what's next? Our next step. Yes, I'm going to put this on a line. And the reason I'm doing this is so that I can very clearly see what's going on. Here I have my -2, here I have my 0, and here I have my 2. Now if I try to look at the first derivative at each of these points, I'm going to end up with 0, so I'm going to pick points around them. a good point here would be -3. Here would be -1, 1, and 3. Now I see that you said plug it into f of x. Am I plugging this into f of x? Is that where this is going? And if so, why? We're checking the sign of something, yes. But is it the sign of f of x? What will the sign of f of x tell us? Sign of f of x will tell us if we are like a positive number or a negative number, right? So like if x is equal to 1, then are we up here or are we down here? It's not going to tell us how our function is changing. And if we want to see how it's changing, if it's increasing or decreasing, for instance, what are we going to use? F prime of x, exactly. So this number line we're working with right now, and like the red and orange, this is going to be our critical point number line. And we want to see how it's changing around these critical points. At -3, I'm going to have a negative times 9 minus 4 is positive. So I'm going to have a negative times a positive. So this whole thing is going to be negative. I'm going to draw that as a downward facing arrow. And then a negative times 1 minus 4 is a negative, so I'm going to have a positive. Yep. Here we'll have a positive times a negative. And then here we'll have a positive times a positive. So I've drawn it like this, not with positives and negatives up here, but with arrows, so that we can pretty clearly see the direction that this is going. So we can answer 2 of these questions up here now. What 2 are we going to be able to answer? And kind of get, yep, okay, max and min. So where is our maxes and where is our mins? Yes, we're gonna have a maximum at 0. And we're gonna have mins at 2 and -2, yep. So we're gonna have a max at x is equal to 0. We're gonna have min at x is equal to -2, x is equal to 2. Now, if I wanted to find the absolute max or the absolute min, probably wouldn't be able to do it, because my guess is that this function is going to go off to infinity in either one or both of those directions. But the idea would be that we could then plug these x values into our original function to find out what the coordinate point is. For instance, this could be, you know, like 0, 4 or something like that. It's actually going to be 3. This point is going to be 0, 3, and so on and so forth. So what's the other question we can ask? Oh, yeah, somebody already answered it. It's increasing and decreasing. So where are we increasing from? What are the intervals on which I am increasing? I am increasing at the x value -1, but yes, the intervals I'm looking at is I'm increasing between -2 and 0, and then between 2 and infinity. So I'm going to be increasing from -2 to 0 and 2 to infinity. Okay, now what about decreasing? You can do this in a different color. Do it in green. Yes, so I'm going to be decreasing from negative infinity to -2. So this area here, and then between 0 and 2. Awesome. So now we have established where our mins and maxes are and where we are increasing and decreasing. We have 2 out of these 4 set up. The last 2 are going to be, they're going to require a little bit like different stuff. So I erased all of that. Now I need to look at how to find concavity. How am I going to find concavity? Yes. So I'm going to take the second derivative, which, as you said, is going to be 6x squared minus 8. And then I am going to rearrange it in a little bit different of a way because I want to be able to see it a little bit better. Factor out that 2. We're going to look at 3x squared minus 4. That's not great. Not a huge fan of that, but I'm just going to leave it as it was. Okay, so how am I going to use this to find concavity? What do I need? Yes, I'm going to need x values. At what are those x values going to be? What are we going to try to find? Well, what are those? So, like, how did you find them? Let's start with that. Okay. Okay, but we're gonna have to set this equal to what in order to do that? 0, yes. So we're gonna say that this is 0 is equal to the second derivative. And these x values are going to be not just any x values, but they're going to be the x values at which the concavity changes, right? So I can like divide by 2 and I'm going to end up with 0 is equal to 3x squared minus 4. I'm going to get 4 is equal to 3x squared. I'm going to get 4 over 3 is equal to x squared. I'm going to take the root of that and I'm going to end up with, what are these points called, these x values? Their official name, point at which concavity is going to change. Inflection points, but yeah. So this is going to be at x is equal to minus 2 over root 3, and x is equal to plus 2 over root 3. Or I would believe that's 2 root 3 over 3. And 2 root 3 over 3. Because people don't like having square roots in the denominator. It's just not a thing people enjoy, like math people. So they move them up to the numerator for whatever reason. But here we have it. We have two inflection points, a negative and a positive. What is my next step? I have these inflection points. I need to use them to do something. What is it that I'm going to use them to do? Yes, we're going to do the same type of number line, but we are going to use these points exactly. So we're going to have negative 2 root 3 over 3, and we're going to have positive 2 root 3 over 3. And I'm going to check exactly what that is so we can pick numbers on either side. And that's going to be about 1.15. So a good number on the inside is going to be 0, obviously, and then we're just going to do 2 and negative 2. Okay. So we're going back all the way over here. We're going to see, is it positive or negative if I stick 2 into this equation? So that would end up being a positive times 3 times x squared is going to be 4 minus 4. So that's going to be 3 times 4 minus 4, which is going to be a positive number, right? At 0, it's going to be 3 times 0, so 0 minus 4, which is going to be a negative number. And then it's going to be, again, 3 times 4 minus 4, which is a positive number. So, are these mins and maxes? Yes, these are not mins and maxes. These instead are telling us what? Yes. Where am I concave up and where am I concave down? On what intervals? So I'm concave up from negative infinity to negative 2 root 3 over 2. And then also from 2 root 3 over 2 to infinity. Yep. And then I'm concave down between negative 2 root 3 over 2 and 2 root 3 over 2. So here's where I'm concave down, and here is where I am concave up. Is everybody okay with what we have just done? We have found our critical points. We have found our inflection points. We have found our maxes and mins based off of our critical points and our increasing, decreasing based off of that number line. And now we have found our concavity based off of the number line we generated from our inflection points. If everybody's okay with where we're at, then I'm going to erase some of this. And we're going to hop into drawing this. I'm going to move our inflection points, I think. I don't think I can, like, select. Maybe I can. Oh, how convenient. Okay. That's no problem. We'll work through that right here. because concavity can sometimes be a little bit difficult to like look at on a graph, and you're thinking like, what's on earth happening here? I like totally get it. Okay. So now actually, because we're sketching this graph, I would actually go through and I would suggest finding out what these points are. So for instance, what is my y value when x is equal to -2? How would I determine that? Yes, so I'm going to say that I have f of -2 is going to be 1/2. What is -2 to the 4th? Yep, positive 16, and this is going to be 4 minus 4 plus 3. So this is going to be 16 over 2 is 8 minus 16 plus 3 minus 8 plus 3 minus 5. So this is the point, -2 minus, comma, minus 5. And here it's going to be something very similar because x to the 4th is again 16 and x squared is again 4. So we're looking at the point 2 minus 5. So now I've got these points. And I'm going to go ahead and plot those because I think that would be good. So that's 5, 4, 3, 2, and 1. That'll be -5. We'll do the same in the opposite direction. +5. So I have the point 0, 3. So my x value is equal to 0. My y value is equal to 3. This is going to be a max. I have the point here's 5 and here's -5. I have the point -2, -5. And I have the point 2, -5. So those are 3 points that I know exist on my graph of f of x. And I know that those are mins and maxes. Next, I'm going to go ahead and sketch out a little bit of what I know about my increasing and decreasing at this point. I know that from -2 to 0, I'm increasing, which makes sense. So I'm just kind of drawing lines, and I know that from 2 to infinity, I'm increasing. So this is like stuff that I know. This doesn't look exactly right now, but I do know that I'm increasing and I'm getting a general shape. I know that I'm decreasing. My function is getting smaller as the x value gets larger. Between -infinity and -2, and between 0 and 2. So now we can kind of see what the shape is, but we're missing the concavity. So I am concave up. So we said this is going to be about -1.15, and this is going to be about +1.15. So this point is 2 root 3 over 3, and this point is -2 root 3 over 3. Okay? Which means that from here to here, I am concave up, and from here to here, I am concave up, right? And what does concave up look like? It's going to look like I have a curve that looks like that, right? Something along those lines. Now, if I wanted to go through and plug in my inflection points, I could say that I have f of 2 root 3 over 3 is equal to 1/2, lordy, 2 root, I'm just gonna do, this is gonna 2 over root 3, because I don't have that kind of energy, so that's gonna be 1/2, it's gonna be 16 over 9 minus 4. Going to be 16 over 9. No, that's going to be 4 over 3. That's going to be 16 over 3 plus 3. So I could go out and do this math. So this becomes 3. This is 16 over 18 minus. That's incredible. I don't like that. Anyway, you could do this. You just need to find the common denominators. So that's 16 over 18. I love how I said I wasn't going to do this, and now I'm totally just doing it. 25 over 3. You'd multiply it by 6, so that would be 150. 16 minus, oh, that's crazy, 150 18ths. And so on and so forth. But you'd get a number probably around here-ish, based off of how we drew what we're doing. If you were doing it on a test and you had the time, I would recommend doing this and finding out exactly what those points were. For now, it really doesn't quite matter, because what we care about is this X value, and your professors are not going to come after you for your inflection points not being, you know, exactly right. But we know that we have to go from here to here, and we need to be concave up the whole way. So curved inward and curved like that. And the same thing goes for over here. I know I'm not the best artist in the world, and it can be a little klutzy sometimes, but this is essentially what we're looking at. So there's our concave up. And then we know we have a point where it's concave down, and that's in this area right here, between these two inflection points. And we know the general shape is going to look a little bit something like this. So this is our final graph. This is it for like this problem. This is what they would ask you for. My issue with my drawing is that sometimes I can get the lines look a little too straight or a little too like curved in on themselves, and that's really difficult to like show concavity then if I get the curvature wrong. But the idea is that this is concave down and this is concave up. So does anyone have any questions? This is like, my calc professor loved these, having these on exams, having everyone do them. Because they make you use a lot of skills, they make you find a derivative, they make you think about graphing and concavity and all that jazz. Okay. Does this help the person who asked about graphically determining concavity? Because this did help a little bit. It is sometimes kind of hard, especially if you have like a very small, like I'm thinking of a graph that maybe looks a little bit like this. I don't know what that looks a little bit like this, and like, where do we switch? Because this looks pretty concave down, and this looks pretty concave up, but the idea is that there is a point in between here where it switches from being a concave down to a concave up. So it can be a little bit confusing. Just you can find your inflection point if you have. Yeah, that's true. A good, like, if you have something that looks like this and you're like, God, I don't know, a good place to go is around like the middle. Unless you have like a very slight concave down or like that, and then it, you know, looks like something like this. It might be up here. I don't know. But a good place to guess is always about the middle. So if they give you a graph, just guess the middle. Yeah. Any other things that people would like to go over? Yes, there very likely will be. Would you like me to try to find one in the book that is kind of representative of that? Or do you have one in mind? Okay. That's section 2.8, I believe. Let me scroll there real fast. Know that there is one. There's plenty of examples of relative rates in the book. It's just a matter of finding you wanted to do a cylinder. Would you like to do a cone? Oh, sweet. You can, I think you can attach a file via the chat, or you can email it to me and I can go check my email. I mean, like, this midterm review is all yours, guys. If you guys want to do a related rates problem, we can do that. I can also, the quiz it's from is the related rates quiz, presumably. I can go see if it crops up for me. I think the questions are randomized. You know, I barely know how Canvas works, so. Yeah, I don't think it's gonna give me. Yes. Why don't you, do you have an example of like a limit that you want to work through? I don't remember if it was this class or if it was the other calc class I was working on. One of them, I think, had an exam that had limits that used L'Hopital's rule, which is not something you guys have to know. If you remember it from high school calculus, you don't need to know it. But do you know which sample exam that's on? Okay. Such as problem 8 on exam version B. The limit, oh, there you go. As x goes to negative infinity of 3 roots x, the third root x to the 6 plus 1 over x squared. Okay. Oofda. Does anyone have any strategies on how to do this? Yeah, because it's 0 over 0. Negative infinity over negative infinity. It's an infinity over an infinity. This is not something that you should have to do. Right? Yes. I don't think you have to know how to do this. I'm not sure if you do know, like you might know how to do this, but I don't think it's like this class that walked you through it. I also am looking at the answer right now, and it is, I'm not sure what's happening then here, but yeah, I'm making a face right now, which I think is, I mean, don't quote me on this, but this is not something I would expect to see. You know, I'm going to say that and it's going to pop up, but I can't think of a way to solve this that you know is my issue. And I might be missing something, but I don't think I am. Okay, let's try to do a related rates problem before we wrap up. It'll probably take us about 15 minutes to do a related rates problem. Did you find one that you would like to do, or can we just pick one from the exam or from the book? No, you're good. You're good. Do you mind if we do a cone instead of a... I can find my book. Where did my book go? There it is. We have... Which sample exam? from sample exam B. Okay. So is this sample exam B, or is the sample exam A? The one with the landscape architect? Exam 1? Why would it be there? I guess maybe it's an open. Yep, there it is. They did. Okay. If I click more, I'm sorry. Once we get. Yeah, I totally forgot that too. So if you guys are looking for more related grace problems, this might be a bunch of new ones. Okay. I have exam 1 sample B number 16. If x is differentiable at x is if f is differentiable at x is equal to 2, which I'm not sure is the problem that you're looking for. Is it the inverted circular cone one? Oh, the inverted circular cone. Okay. Okay, so we have a water tank that has the shape of an inverted, 16. If f is differentiable at x is equal to 2, then f prime, okay.
Hi, can you hear me?
Yeah, I can.
No, you totally had it right the first time. Maybe the numbers are switched around on yours, but it was the water tank one.
Okay, for some reason I have Math 140, Exam 1, Sample B. That's number 21.
Yeah, for this one it's number 21 from our section, but maybe yours is a little different. But you had it right. It is the one with the inverted circular cone.
Okay. 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 I don't know why that is. I'm not a huge fan of that. I'm not going to think more about it right now. But we have an inverted circular cone. I'm going to draw it. Like so. It has a radius. R is equal to 4 meters. And it has a height. H is equal to 6. meters. If water is being pumped into the tank, this is not water leaving the tank, this is water going into the tank. I should put the whole question. Closing the bottom there. Water is going into the tank at a rate of, hold on. At a rate of 16 meters cubed per minute. Finds the rate at which the water level is rising when the water is 3 meters deep. So, basically, what do we have here? We have a small cone inside of a large cone. We have dV/dt. What is dV/dt? Yep. Okay. What else do we have? We have our radius. We have our height. What is it that we want in terms of like math language? The rate at which the water level is rising when the water is 3 meters deep. So I have two statements here, I think. First, we want the rate at which the water level is rising, exactly. That is dH dt. But we only want it when what? X is equal to 3. Awesome. Okay. So now we have what we have. We know what it is that we want. We need an equation that can link this all together. What would be an equation that would link this all together? The volume of a cone. Does anyone know what the volume of a cone is? In the copy of the exam I'm looking at it, they give it to you. I wouldn't trust that it would be given. I would know the equations for a cone, the volume of a cone, the volume of a cylinder, the volume of a sphere, a cube, etc., etc. But the equation that they give you on this exam is 1/3 pi r squared h. So, what does this mean? What can we do to this to end up with something that includes the pieces that we want? Also, this is, it's not x, it's going to be h. Yes. Because again, we're actually going to be, sorry, I'm like thinking through this a little bit. This is the cylinder that or not cylinder, this is the cone that we're mostly concerned with right now. So to make R in terms of H, what are we going to do? Like, how are you going to do that? We have over here VDH, DH, DT. Okay, sorry. Similar triangle, okay. Yeah, you can do that. So what you're saying is that when we have the triangle that looks like this, that is 4, 6, and then, you know, Z, we can have a similar triangle that is 3, R, and Y. I'm not sure if that's exactly what I do. I think we should, not sure if that's where I would start right now. Okay, let's go back to well, you can do that. I'm crazy. I added too many variables. This is fine. You were on the right track. I'm just sorry. I really struggle with related rates just because it takes a lot to put it together. So similar triangles, it's just a ratio, right? I can just say that 6 over 4 is equal to 3 over R2. So that would be 6 over 2 is equal to 12, R2 is equal to 2. That's not general enough though. I'm missing something. Does anyone know what I'm missing? There we go. That makes sense. So we rearrange this for R. We say that this is 6R is equal to 4H. R is going to be equal to 4 over 6 is going to be 2 over 3H. And that is going to be general. So this is going to be able to be applied to any cone that is within this cone. So now I can put it in this equation, and I'm down to 2 very reasonable variables. We have V as a function of H. Awesome. Okay. So what's my next step? now I'm unmuted. Sorry about that. I didn't have internet for about, 3 minutes there. Not sure what happened. So sorry. Also lost all of that work, but that's fine. We can put it back up. Does anyone remember what the equations were? But why are you apologizing? I'm the one who totally lost connection for a hot second. Here is our cylinder of water. This is happening at 16 meters cubed per minute, which is dV dt. We decided that our equation is going to be V is equal to 1/3 pi times 2/3 h squared times h, which turned out to be 4 pi over 927 h cubed. Okay, at an angle. But we have our equations now. We just basically have like one more thing left to do. And what is that going to be? Knowing that what we want is the h dt when x is equal to 3. H is equal to 3. Yes. What are we taking the derivative with respect to? This is going to be d dt. So we're taking the derivative with respect to t of v, and like of this side of the equation, we're basically implicitly differentiating. So we'll have dv dt is equal to ddt 4 pi over 27 h cubed, which is going to be 4 pi over 27 times 3 h squared times dh dt. So this is going to end up being dv dt is equal to 4 pi over 27 times 3 times h squared times dh dt. And now we essentially have all of the parts that we need. We have these constants in this dark red, we have our dv dt, and we have our h squared. So I'm going to just start plugging stuff in. We're going to have 16 meters cubed per minute is going to be equal to, that is going to be 4 pi, and I'm just going to do this. I'm going to make that 9 and cross that out. That'll be 4 pi over 9 times our h is equal to 3. So this is going to be times 9, 3 squared, times dh dt. And this is not going to, this is 3 meters. So this is meters squared. So I'm going to smash these together and I'm going to end up with 4 pi meters squared times dh dt. then I am going to divide, essentially. By this whole thing gets divided by 4 pi meters squared. That means this side also gets divided by 4 pi meters squared. So 16 divided by 4 pi is going to be 4 over pi. And my units are going to be what? Meters per minute. Perfect. And that is going to be equal to dH dt. Does this answer make sense? Awesome. Why? What makes you think that it makes sense? How we found it, but also a good final check, those units. We got meters per minute. Height is changing with respect to time. Well, good. Okay, sorry about that little interruption in the middle of the session. I unfortunately do have to go, but I hope this was helpful. Does anyone have any last minute questions about this? Thank you guys so much for coming. I hope your midterms go awesome. In terms of most important area, I don't write the exams, unfortunately. Related rates are going to be important for you, and taking all of those new derivatives that we learned and increasing and decreasing and really getting familiar with first derivatives and second derivatives is what I would say is all very important. Unfortunately, I don't have a more direct answer. I'm sorry. But I do hope it goes very well for you, and I hope to see you next week. Have a good one.